Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we will be looking at GCSE Biology, Osmosis. Last time we were talking about diffusion. How particles move down the concentration gradient from area of high concentration to area of low concentration. Today we will be talking about osmosis, where osmosis is essentially a special case of diffusion. That's all it is. Osmosis is just a special case of diffusion. Don't worry, I will explain everything. I will explain how it works, and I will explain an experiment that's often used to show that osmosis works. So, if you haven't seen a video on diffusion, it might be worth for you to check it out. I put it down for you in a link description below, so if you want to know more about diffusion, just check it out. Anyway, for osmosis, without further ado, let's get started. Now, what is osmosis? As I said, osmosis is a special case of diffusion, where in osmosis we are talking about water. In diffusion, we were always talking about solute. We were always talking about the sugar or about molecules that are within water, and we were talking about them moving across membranes or just moving from area of high concentration to area of low concentration. Now, in osmosis, the difference is that we are talking about water. Everything in osmosis is about water moving from area of high concentration. I'm gonna write it down for you. To area of low concentration. And we always, in osmosis, according to definition of osmosis, it is a movement of water from high concentration to low concentration down the concentration gradient across a semi-permeable membrane. Okay, so that's my sort of picture that, should help you quickly remember definition of osmosis. And here I drew a picture to sort of explain it in more detail. So here we have in blue we have molecules of water, and in red we have sugar. We have sugar molecules, and here we have a semi-permeable membrane. Very similar to the way we were talking about last time. And when we are talking about diffusion, we'll be talking about these guys, the sugar molecules, wanting to get across to this side to area of low concentration. However, we are talking about osmosis. I want to make this crystal clear because there is a lot of confusion about this. So, we are talking about water in osmosis. So, as far as osmosis goes, we are talking about these guys, blue guys. And here we have a lot of water, a high concentration of water. And here we have less of water because it's mixed with sugar. So the net movement of particles will be to this side. These molecules of water will go over here to sort of attempt to even out that water concentration. Now, those particles they'll be moving both ways. So these guys can go there, these guys can go there, this guy can go back, but this guy can go back in. So they are moving across. However, the net movement, the overall change in number of water molecules will be that there will be less water molecules here, and we will gain some here in attempt to even out the concentration of water in both sides. So that's what essentially osmosis is. Again, I will remind you, osmosis is a movement of water molecules from area of high concentration to area of low concentration across a semi-permeable membrane. That's the definition of osmosis. Now, so the concept is simple enough. It's like diffusion, but it concerns water. The way to avoid any mistakes, is to have this crystal clear in your head. When you're talking about osmosis, we are talking about diffusion for water. When we are talking about diffusion, We are talking about diffusion for sugars and other stuff. It works the same way, but it concerns different molecules. Okay, so this is how osmosis works. Now I will quickly show you an experiment that's often used to demonstrate this phenomenon of osmosis. So this is often used in schools. You might have done it. It is often demonstrated in exams as well, so I thought it would be useful to explain the experiment. Okay, so here we have 2 potatoes, and the first thing we do with those potatoes is we cut them into chips. They don't have to be exactly equal, but we cut them into chips roughly the same size, but they do not have to be perfectly equal. I will explain everything later. Bear with me. So we have potatoes, we cut them into chips, and then what we do is we weight them. We weight them to gain original mass, because these chips are gonna change mass based on what's happening in terms of osmosis. But before we do this, because I said that they do not have to be equal weight, they do not have to be exactly the same, we need to weight them before. We will have the picture before, and we will have the picture after. Bear with me. So, first of all, we weight those chips to gain original mass. And then, this is all the same, and then that's where it gets different. We put one chip in a container with just pure water, whereas we put another chip in a container with concentrated sugar. And then we leave them there for, say, 24 hours, and then we come back, we take the chip out. Osmosis in there has already happened depending on the concentrations of water. I will explain that later. So osmosis happens at this point, and then we take those chips out, we put them back on a weight scale, and we acquire the final mass. So here we have a picture of before, what they weighted before, and here what they weighted after. Why are we doing this? Why are we weighting the chips? Well, because like I said, osmosis will be happening here, and depending on the concentrations of water in the potato chip itself and outside the potato chip in the liquid, it will either gain mass or lose mass. And therefore, we will show that in the final mass, that the final mass is different to original mass because those chips either gained water or they lost water. But which is which? Which one of these is going to gain water and which one is going to lose water? Well, here I drew this out for you guys. Let's think about this. So, here we have a chip that was put in water. I drew the chip in a dotted line because this is a semi-permeable membrane, essentially. And inside the chip, we have some water, but we also have electrolytes, we have salts, and we have sugars. That's the red stuff. So in water, ultimately, the concentration of water is lower in the chip compared to outside where it's high because it's literally just pure water. So outside we have high concentration of water, and inside the chip we have a low concentration of water. So what's happening here is that the water is moving down the concentration gradient from area of high concentration to area of low concentration. So water is moving into the chip and it stays inside the chip. Therefore, the chip will gain mass. So this chip here, the chip that was in water, will be heavier than it was before. However, if we look at the chip with concentrated sugar right here, again we have our chip with our sugars, electrolytes, salts, what have you, inside it, and water inside it. However, outside, so these two guys are similar. However, outside what's happening is we have lots of sugar molecules, and less water molecules. So in fact, we have high concentration of water inside the chip and low concentration of water outside the chip. So what's happening here is that the water inside the chip is moving from area of high concentration to area of low concentration outside the chip. It's moving out of the chip across the semi-permeable membrane. So that's what's happening. And here, our final mass would be less. So I'm going to write this down here. Lower mass, whereas here we have a higher mass. And that's a very simple way of showing that osmosis works, which is why it's often used in schools, because it's just so simple. It's incredibly simple. Okay, so this is it for today, guys. Thank you again for watching my videos. I really appreciate every time you guys watch my videos. If you want to see daily videos on maths, on sciences, and some biomedical sciences, hit that subscribe button below. If that video helped you, I really hope it helped you, give me a good old thumbs up. Thank you again for watching, and see you next time.